Hi, so this is Mark Weitzman, and I want to continue with some particle physics problems in relativity. Here we're going to do some what are called threshold problems, so let me read it to you. The Berkeley Beavatron, you can see this exercise is about 50 years old, was designed to accelerate protons to sufficiently high energy to produce proton-antiproton pairs by the reaction. Colliding two protons, you get these two protons plus a proton-antiproton pair. The so-called threshold energy of this reaction corresponds to the situation when the four particles on the right move along together as a single particle of mass m equal 4mp. So it's kind of like the minimum energy we need to produce this. If the target proton is at rest before the collision, what kinetic energy T must the bombarding proton have at threshold? So we want this to be at rest, and we want this to be like a single particle, mass 4mp. Okay, so in the lab frame, this is what we have. Before we have the mass of a proton going with velocity v, colliding to a proton at rest. And afterwards, we want single particle, rest mass 4mp, going at velocity v prime. Okay, so you can work these problems in two ways. You can work in this lab frame, or you can be smart and work in the center of mass frame. Center of mass for relativity really is the wrong terminology. It should be center of momentum. Actually, it should be called the zero momentum frame. But I'm just going to continue to refer to it as the CM frame. You can think of that as center of mass or center of momentum. So, in that frame, what do we have? We're going to have a proton. Let's do before. Proton moving at the velocity in the CM. Another proton moving at a velocity in the CM. These two collide, and then let's call this before, after, lab. Let's call this CM. After, we just have a single particle, 4mp, at rest. There's no momentum in the center of momentum frame. That's why we call it the zero momentum frame. So before and after we have to have zero momentum, so we just have a single particle, 4mp at rest. So now it's not that difficult to work out the equations. I'll do it. We'll have 2 gamma CM MP. This is working in the center of momentum frame, so this is just the energy before has to be equal to the energy after. It's equal to 4mp. So that implies that the gamma CM is equal to 2. And this implies the velocity of the center of momentum frame relative to the lab frame. So square root of 3 over 2. Now, the velocity of the particle in the lab, this particle that hits the target particle, we're just adding two relativistic velocities of that magnitude, so it's going to be the square root of 3 over 2. Again, c equal 1 in all these videos, plus the square root of 3 over 2, divided by 1 plus square root of 3 over 2 times square root of 3 over 2, and this is equal to 4 times the square root of 3 over 7 Then if we want to know the energy, we need to know the gamma of the lab, which is equal to 1 over the square root 1 minus 16 times 3 over 49. And this is equal to 7. So the kinetic energy, T, is equal to 7 MP minus MP equals 6 MP. That equals 5.628 GeV. So we would need a proton of 5.6 GeV in order to create a proton and an antiproton pair, which has rest mass of about 2 GeV. So, well, that kind of makes sense. Okay, now to do a comparison, this would be like a proton-proton collider. Let's do the same thing. Except here we'll have electron colliders. So E plus E minus goes to E minus plus E minus plus P plus P bar. P bar is the antiproton. So, and it says for this problem, assume ME equals 0.5 MeV. Just wants an approximation. You'll see why. And MP equals 1 GeV. Okay, so it's almost exactly the same equations as we just had, just a little bit. 2 gamma Cm Me is equal to 2 MP plus 2 Me. So here the 4 particles are together. 2 of them are proton, antiproton, which have masses, rest masses of MP. 2 of them are electrons, which have rest masses of Me. So this gives us gamma Cm equals MP plus Me over Me, which is, using these approximate numbers, about 2001. And now we do the same, this leads to VCM is equal to square root of 1 minus 1 over gamma Cm squared, and VLab equals to this plus this, which is 2 times the square root of 1 minus 1 over gamma Cm squared. I'm not substituting in numbers because there's going to be some cancellations and everything. So I'll just keep the formulas 1 plus the product of these two. 1 plus 1 minus 1 over gamma Cm squared. And then from VLab you can calculate gamma of VLab. This is going to be equal to 1 over square root 1 minus this squared, which is 4 times 1 minus 1 over gamma Cm squared, divided by 2 minus 1 over gamma Cm squared. And if you work out the algebra, it all simplifies to 2 gamma Cm squared minus 1, which is equal to 2 times 2001 squared minus 1. And so this is equal to, this is 8008 times 10 to the 3. And the energy for the moving electron is going to equal to the 1/2 MeV for the rest mass of the electron times 8,008 times 10 to the 3. This is equal to 4,004 GeV, which would have been impossible 50 years ago. Now at the Large Hadron Collider we could have this energy, but you can see I erased the number, but before we needed 5 GeV using protons to create a proton-proton pair. Now we need 4 TeV, 4,000 GeV to create using electrons. So protons are much more efficient, but they're not as clean as electrons. There are advantages of using electrons because these are point particles and very clean. These are complicated hadrons. So I'll do one more production in the next video, and we'll get back to and one more relativity problem, and then that will finish it for this series.